The purpose of this lab was to observe an object falling from rest somewhat slowly, and then to analyze the object's motion, determining the forces acting on the system. Dropping a crumpled up piece of paper, the forces assumed to be acting on it were, of course, the force of Earth's gravity and the drag force, or the air resistance. The gravitational force is the force pulling on the paper to the ground, while the drag force opposes the object's downward motion, acting as an upward force and in this case is in the opposite direction of the system's velocity. To demonstrate the observed motion of the paper falling, two computational models were constructed. One included only the effect of gravity, and the other was based on the effect of gravity and the effect of drag force. Both the models use Newton's second law, or the momentum principle, as a basis for the results. After comparing all the data, the model utilizing the gravity and the drag force best fit the observed motion of the falling paper. To set up my experiment, I recorded a video of myself dropping a piece of paper from rest and uploaded it into Tracker. The coordinate axis placed so that the paper was at the origin and falling in the negative y direction. After tracking the object in motion, a graph was obtained from the data. The graph shows a near parabolic curve, representing the position of the object versus the time it is falling. In this graph, it is evident that the object speeds up as time increases, since the slope of the curve, which is in meters per second, becomes steeper while the motion progresses. The fact that the object increases in speed implies that there is some net force acting on the system. This assumption comes about because of Newton's second law. His law that change in velocity equals a net force over mass times a change in time shows that the net force must be a non-zero vector for there to be a change in velocity. This law is equivalent to the momentum principle, which states that the change in momentum equals the net force times the change in time, once again telling us that F net must be a non-zero vector in order for there to be a change in momentum. Because the mass in this case is constant, that is, that the mass of the paper does not change, momentum and velocity are proportional to each other. If the change of paper's velocity is non-zero, then so is the change in the paper's momentum. This tracker information was used to create the computational models designed to mimic the object's motion. First, the model including only the effect of gravity was constructed. This model was set up using the mass of an 8 by 11 sheet of paper. Also, the initial position and velocity were set to the zero vector, since the system started at the origin and from rest. The paper fell for about 2/3 of a second, so delta t was set to 1/1000th of a second, relatively small compared to the duration of the motion. Earth's gravitational constant, or little g, also had to be specified because this is the basis for the net force acting on the paper. The unit vector j hat was initialized. This was essential information necessary to establish that the object moves in the y direction. The object fell for about 2/3 of a second, and during this time, the force of Earth's gravity, also known as the weight force, pulled the object downward. So in my model, the weight force equals negative m times g times j hat, or the mass of the paper times the acceleration due to Earth's gravity moving in the negative y direction. This weight force equals the net force in the model, since it was assumed that this was the only effect in the object's motion. The motion of the system is downward and increasing, as shown by the position versus time plot and the visual created by the model. This data was compared to my experimental data, and I observed that the model did not truly fit the experimental motion. In fact, it overpredicted the object's position and its velocity. While the model did well to predict the motion early on, as time progressed, the model continued to speed up as the observed system began to experience an acceleration of less magnitude. This implied that there must be some other forces acting on the paper ball. The other forces were possibly the drag force, acting in the opposite direction of the object's motion. To better predict the observed motion, a model was created including the effect of gravity as well as the effect of the drag force on the system. This model included all the same initializations as the previous model, with one exception. A drag force constant had to be included. This constant was determined through trial and error, running the computer code until the final position in the model equaled the final position in the observed data. This constant allowed me to include the drag force in the calculation of the object's motion. The drag force is assumed to be proportional to the square of the magnitude of the paper's velocity. So the constant times the magnitude of the paper's velocity squared times j hat should equal the drag force experienced by the system in the model, which again is in the positive y direction. F net is then determined by both the drag force and the weight force in the system. The drag force slows down the motion and yields this graph and visualization. Comparing these results to that of the observed motion, I found that including the drag force provided a better representation of the falling paper's motion. This model also came close to reaching a terminal velocity. The graph of the model, including only the effect of gravity as the net force, showed that the object continued to accelerate at the same rate throughout its motion, so the velocity continued to increase. This model showed us that with drag force, the velocity of the object will still continue to increase, but at a slower and slower rate. It does not predict a terminal velocity, but it shows us that the object could possibly eventually stop speeding up and reach a terminal velocity. Putting all of my data on the same graph, I was able to analyze which forces were acting on the observed system. Since the results of the model, including both gravity and drag force, gave me very similar data to what I observed, I determined that the experimental falling paper must have experienced the effect of gravity and the effect of air resistance when dropped from initially at rest. To answer the what-if question, I parameterized the gravity and drag force model so that it ran for a longer time. I ran the model for 4.5 seconds and for 5 seconds, printing the final time and velocity data. At both times, my velocity was equal, telling me that the paper had reached a terminal velocity of negative 5.563 meters per second after being dropped from rest. Changing the initial velocity from the zero vector to a vector with an initial velocity of 1 meter per second in the downward y direction, and following the same procedure, I found that the paper reached the same terminal velocity of negative 5.563 meters per second as when it was dropped from rest. I found that no matter what velocity I started the model with, the paper eventually reached the same terminal velocity, given enough time. So in conclusion, Newton's second law and the momentum principle can be used to predict an object's motion in the future. Using these fundamental principles, we were able to determine what forces were acting on an object dropped from rest. Our results gave us that the falling object, no matter what velocity it starts at, will experience the effect of gravity, and with the effect of a drag force, reach a terminal velocity at which the system will cease to accelerate. When the terminal velocity is reached, the net force on the system will have reached zero, where the forces of gravity and drag, as well as any other outside forces, sum to zero. The momentum principle explains the phenomenon, and it is reinforced by Newton's second law.